Hi everyone, I'm Ilane Schroetter and I'm a contract researcher at IRAP in Toulouse. And today I will talk about the role of external UV radiation on protoplanetary disks with GWST. So to begin with, what are protoplanetary disks? Basically, they are circumstellar disks rotating around a young star, which is here, and in which future planets will fall. This disk is separated in a few areas, and this is like this room, the snow line. I mean, like further away, the water freezes, and inside it's still in vapor. So you have the inner disk in which telluric planet will form, and in the outer disk where giant planets will form. Now, I would say, like in galaxies, those kind of young star doesn't pop up like that, like isolated and stuff. So they usually are formed within the vicinity of clusters. And in those clusters, they usually have massive stars. Those massive stars create UV radiation, and those UV radiation interact with the outer disk, creating the photoevaporation. So what we want to do with GWST is trying to constrain the physical and chemical impact of UV radiation on those objects. Let's go back to reality and have a nice plot. And I don't know if yeah, you can see so this is the 2D probability density of a star to form as a function of the UV radiation and the number of stars. Meaning here you are basically isolated and you have very low probability to form in this area, whereas in the Orion Nebula cluster, for instance, you have massive star, etc., and you are more likely to form in this area. Two examples are for the GWST, from GWST MIRI spectrum from 5 to 20 microns of, this is an isolated disk. And you see that there is weak emission lines or no emission lines at all. And you have also neutral species like CO2, HCN, etc. If we look at UV irradiated protoplanetary PPD spectrum in Orion, you can see that the shape is completely different. For instance, you have strong emission lines, and also you have ions and radicals. I will come back to this spectrum later on. Also, it was mentioning that from very recent reviews, the solar system has been formed in high UV radiation area. So meaning understanding the UV impact on protoplanetary disk will basically help us understand how our solar system formed. The data that I'm using is the data for PDS4O. This is an early science program with hundreds of collaborators from many countries. It has around 40 hours of GWST observation with NIRCam, the imager, MIRI imager as well, and it has also NIRSPEC and MIRI MRS observations. You have more details in pds4.org. And as an example, you have, those are the publications that has been published the last 2 years from those data. What I want to present to you here is basically what we do in Toulouse. This is a GWST team in Toulouse, led by Olivier Bernet. Landry Marquis and Paul Amiot are 2 PhD students, and Amélie Cana is a research engineer. And in Toulouse, we are leading the study of protoplanetary disk. And specifically those two. And in this presentation, I will present both of them. 203-506, which is this one at the bottom, and 203-504 at the top. I will begin with 203-506 here at the bottom. this is the near spectrum of this object. It goes from 1-ish to 5-ish micron. And you can see that this spectrum is very, very rich. You have OH emissions, CH plus, CO as well, a lot of molecular hydrogen in yellow, and a lot of H1 as well. Here I will only present the first results from this very rich spectrum using the molecular hydrogen in order to have the physical impact of UV radiation on photoevaporation. Basically, this is the intensity of H2 transition. So the 29 transition that we've seen just before are here. And the lines are Meudon PDR codes and models for small and large grain. This code gives us the gas density and the gas temperature of this object. Basically, it will give us the mass loss rate due to far UV photoevaporation. And in this particular case, it's up to an Earth mass per year. So it means that it will prevent the formation of giant planets, for instance. For the mirror spectrum that you've already seen just before, again, from 5 micron to 20 micron, you have in the gray area the position of the pHs, the polycyclic aromatic hydrocarbons. You see that they are present here, and almost everything in this spectrum was kind of expected in those kind of environment. But in this specific area around 7 micron, if we zoom in, we can see there is a signature that we couldn't understand at first. And thanks to PCMI in particular, it was easy for us to start a collaboration with spectroscopists in order to decipher what is this signature. And it turns out that this signature was CH3+. And you can see in black the continuum subtracted emission from the object, and in blue, the model. You have a zoom here, and you can see that this model reproduces almost every tiny emission. There will be more information about CH3+ on Wednesday with Marion's talk as well. And as an example here, I won't go into details into this specific plot, but just to show you that the CH3+ is in the center of all. And I think Elliot will talk also on Wednesday on the product of CH3+. So what we learned about this object is that the CH3+ is a product of UV-driven chemistry in the outer disk. And in d203-504, it is the third most abundant species after H2 and CO, meaning the organic chemistry is probably strongly linked with CH3+, as predicted like decades ago. So the future survey with ALMA and NOEMA will search also for products of this CH3+ in UV-driven chemistry. So now we have kind of more details on the outer disk, on the composition of the outer disk of such object. And if we take a slice of it, much more detail. So you can see that the UV radiation here triggers the photodissociation region, so photoevaporation, where you can find pH, CH3+, CO, etc. in the outer disk. For the last part of my talk, I will focus now on 203-504, this one. Also, this is a Muse narrow field mode image, since we cannot resolve it with James Webb too bright in the infrared. Here I stitched NIRSPEC and MIRI-MRS data. NIRSPEC goes from 1 to 5 micron, and MIRI goes from 5 to 20, well, 27 to be precise. And here you can see that the spectrum looks completely different than the previous one. But we can see that we have PAHs in emission here in green. Also, if we look, we have the CH3+ as well. So we have detected in this object also what's going on in the outer disk. But what about the inner disk? And this spectrum tells us a lot about that. Here you can see an emission around 3 micron, which corresponds to the inner disk heated by the accretion process onto the star. And it creates this bump at around 1000 Kelvin. If we look into this spectrum, we can see both water and CO in absorption. What I did here is like same color as before. I constrain the temperature and the column densities of water and CO. Those are the well, it is constrained. Sorry, I missed my word here. So the water and CO are seen in absorption, and they are seen against the viscously heated dust emission. And the temperature of those molecules is around 1000 Kelvin, which is similar to this one on the inner disk. Also, we constrain the column densities of both those elements. And in the inner disk, the C2 ratio is 0.6, which is also the solar system. So now we have a new view of the externally UV irradiated protoplanetary disk, where UV radiation creates like photoevaporation, when you can see the pHs, CH3+, etc. And now we have a more accurate vision of what's going on in the inner disk, where you have more, let's say, pristine gas, where you have like water vapor here in the inner disk and CO, and it will probably create like telluric planets as well here. So this is my last slide. So we've seen that the outer disk, the UV, is triggering physical like photoevaporation and chemical changes. The inner disk looks like it's less affected by the UV radiation. So more simple chemistry, and will eventually create terrestrial planets. This gives us new hint about how our solar system forms as well. Also, our result opened up new branches of observation. So we need the need for more spectroscopy of such objects with WST, for instance. And also people are looking for CH3+ in their data now that we have the signature of this molecule. Also, many more GWST proposal on protoplanetary disk has been accepted as well, also with ALMA and NOEMA. And next February, we will have around 70 more protoplanetary disk spectra using NewSpec. And also as a follow-up from those observations, I just submitted a proposal called MIRI Spectroscopic Atlas of Irradiated Disk in Orion, which focus on those objects with MIRI to get the chemistry. And with that, I thank you for your attention.